Wavelets. So the primates are used in computer vision, but some prefer wavelet decompositions. The wavelets are mainly used for decomposition process. Wavelets are also a filter that localizes the signals in space as well as frequency domains over the different scales. Mainly it is used in multiple scales or resolutions. If you want to perform the data at multiple scale or multiple resolution, we can go with wavelet. So it is used to decompose the image or signal into set of different frequency bands, also known as a subbands. And wavelet provide a better frequency separation. It can preserve both spatial as well as frequency information. And here you can see four images. In first image A is a single level decomposition and B is a multi-level decomposition. I said earlier, right? A wavelet is used to represent multi-scale representation. So this is multi-level representation. So the first one image is split into four parts: low, low, high, low, low, high, and high, high. So these are the single level decomposition. LA means low pass in both horizontal and vertical direction. HL high pass in horizontal and low pass in vertical. LH means low pass in horizontal and high pass in vertical. And HH means high pass in horizontal and vertical also high pass. So let me write it clearly. So image is split into four parts. One is both are low pass, both horizontal as well as vertical are in low pass only, low pass frequency only. High L means high pass in horizontal and low pass in vertical. LH means low pass in horizontal, high pass in vertical. HH means both horizontal as well as vertical are in high pass. So one thing we need to remember: low frequency means we can uh, get the smooth image. High frequency means we can get sharp and finer edge details. Okay, so these are the four images. You can say that a single level image with horizontal, vertical, and diagonal detail wavelets constructed using Pramik wavelet code. So this B is multi-level decomposition. We know that LL provides a low pass application, low pass filter applied image. So the multi-level decomposition means in level one, the image is divided into four parts: low, low, high, low high and high high. This low image alone will be considered, and this image a single image is divided into four, and the divided first image low image is considered again for level 2. Now this will be considered as a single image. Further it is divided into high low high, high high, right? So in the level 2 image we got LL. So level 3 also we will get the same. So low, low high, high high. So here we have performed three levels of image. That is what represents. The top left represents the original image, and these four represents the four images. So like this, one, two, three, four, right? So similarly, this is the first part of decomposition. Then this first low pass alone is considered, and it is further divided into four parts. So and the level 2, after level 2, this first one is again further divided into four one. Now in the next level we will consider the same image and we will divide the same into next level. This is known as multi-level decomposition, and it is closely connected to the pyramids. It can be applied in computer graphics, and it can be applied for computer vision tasks, and it is used to provide a multi-resolution or multi-level representation. Just an introduction about wavelength again. And in this image, a 2D wavelet decomposition is mentioned. Two-dimensional wavelet decomposition is represented. So consider the image A. It is a high level diagram. High level diagram. B is nothing but a separable implementation. In high level diagram, what they have mentioned is, remember H represents high pass filter. High pass filter means it will keep the high frequency. Low pass filter means L. Okay, so input image, will give the input image. Input image is passed to high pass filter as well as the low pass filter, and it is downsampled by two value. Downsampling means image will be reduced, right? So reduce the resolution of the original image, and finally we are getting L1 here, and the remaining usually image is divided into four parts: low low, low high, high high, and high low, right? So this low pass is represented as L1. So remaining LH, HH, HL is represented there because the high pass filter maintains all the low high, high low. So low pass filter keeps only low low. Okay, this is only low low value. So this provides the more coarse in details. Okay, in this pyramid, the last part represents fine details. The top part represents only the reduced details, that is known as coarse details. When applying a low pass filter to an image, we'll get only the coarse details. When applying high pass filter, we get the fine details. So the right side of the image is the reverse passes. L1 upsampling and I and F. I and F are the reconstruction filters. Reconstruction filters. So H is a high pass filter always. H is a high pass filter, L is a low pass filter, and I and F is also known as a filter in order to reconstruct the original images. Okay, so the right side of the image is a reverse process. It will result in the perfect reconstruction. Now B is a separable implementation. So we will apply horizontal as well as vertical filtering here. Horizontal as well as vertical filtering here. So instead of directly passing high pass filter, I am going to apply horizontal high pass filter and horizontal low pass filter. I am going to perform downsampling on horizontal filter alone. Only the horizontal values will be considered. Then the resultant could be applied on the vertical. Okay, so HV, LV, HV, LV represents high pass filter on vertical value, low pass filter on vertical value. Then I'm again going to perform downsampling on vertical. The resultant would be the same four values: low low, low high, high low, and high value. So the same is inversed here, that is known as inversed transform. So low level will provide only the coarse approximation. Remaining all the three levels will provide the fine details of the images. So this is known about separable implementation. And some major or common differences in pyramids and wavelets are discussed here. Traditional pyramids will keep more sample than original images, but the wavelet doesn't provide any additional samples, so there is no redundancy here. And no redundancy here. Pyramids give the frequency a general frequency split. There is no separate horizontal vertical split, but in case of wavelet, we can divide the images into horizontal component, vertical component, as well as a diagonal component. And 2D wavelet decomposition is done by using low, high, low, high, the 3 by 4 of the images, and 1 by 4 corresponds to the low level. It is only passed to the next decomposition stage. Low level part alone passed to the next decomposition stage. So the next one is one-dimensional wavelet transform. So previously we have seen two-dimensional wavelet. Now we are going to see one-dimensional wavelet transform. In one-dimensional wavelet transform, so we are going to apply the same process. The first we know, right? But the one change here is this is, the input image is passed to high pass filter, low pass filter, and I'll tell you what is this ORE. So on downsampling we are getting images. So this represents low frequency, this represents high frequency. Simpler. Previously we have divided into four, right? That's not right here in case of one dimension. So the reverse process is also explained here. Now the alternate one, it is known as lifted version. Okay, so a lifted version. In this lifted version, initially we should not pass the data to the high pass filter or low pass filter. Initially the input image is divided into odd sample and even sample. O and E represents odd and even sampling. Instead of applying two filter high and low, we have to perform down sampling and then we have to perform L stage and C stage. L stage is used to predict the odd samples. So we can use the even samples to predict the odd samples. So this level represents odd, this level represents even. Okay, input image is divided into odd sample and even sample. So the even sample is given to L phase, okay, L, and the L is used to predict the odd value. So it is predicted value of odd sample is there, and originally odd value, the image having odd samples and even samples are divided. So the predicted as well as original is subtracted to identify the error or to understand the differences. Then the predicted odd is again given to C stage to predict the even samples. Then the result of this would be L1, and the result of this would be H0, which would be the same. Both this represents low and this represents high frequency details, and the inverse is represented uh, in the right side of the image. That is what mentioned here. The figure here represents usual high pass and low pass filters, but followed by odd and even down sampling. This B diagram is known as lifted sampling, which first select the odd and even subsequence and then apply the low pass prediction stage and high pass correction stage. Sorry, the C is not prediction, it is correction stage in an easily reversible manner. Okay. And this diagram represents the lifted transformation of a signal processing. Okay, lifted transformation of a signal processing. So here we have a set of signals. First, in case of lifted transformation, what we'll do, we'll divide the data into or signal into even samples and odd samples, right? So only the even samples are considered into the next level. Okay, so this is what mentioned. Mm, okay, so initially we will divide the data into even samples, and then using the even samples we will predict the odd one. Okay, you see this diagram, and the input is divided into even and odd. The even is given as an input to the L, and this L is used to predict the odd. Okay, so first the even is determined, and using the even we are going to predict the odd values. And then now you see the level 1 2 3 4 5, only the 5 data is there. In this step, perform the step again, determine the even values alone, and based on the even values calculate only the odd values. This is the lifted transformation. So the same but in the reverse process, from down to up is represented here, the same, but in this here we followed top down, here we are going to follow the bottom up process. The previous diagram is represented here. We first divided the inputs into odd and even samples, and in L filter we have used the even samples to predict the odd sequence, and to understand the differences between both predicted as well as original, we are going to subtract the predicted value and original value, and to update step is C filter. Use the high pass coefficients to update the even sequences. Ensure that even sequences represents the low pass coefficient. The result of the even would be L, right? It is low, and because odd and even samples are updated correctly, no large temporary buffers are required. So it performs in-place operation, no additional out-place operations happens. Multiple lifting means by chaining predict and update, you can design the wavelet with desired frequency response. Then when you perform even sample, there will be an aliasing in even sample. So to compensate for aliasing in even sample, a small amount of high pass wavelet is added back to properly low pass filter the even sequence. And the low pass filter and high pass filter operations can be interchanged, which means previously we have divided the even to predict the odd, right? So both operations can be interchanged. We can predict even from odd also, which means this can be interchanged. This can be interchanged. First we can perform C and then we can perform L. So we can use odd sample to predict the even. Okay, let me write it clearly. So we can use C to predict E, and then we can use the same to predict the odd samples. that would result in high as well as it would result in low. That is what mentioned here. So we can predict even from odd, odd from even. Both filters operations can be interchanged. So lifted wavelets or second generation wavelets, it can easily adapt to non-regular sampling, and it is highly effective for local image manipulation. And instead of common separable wavelet approach which decompose the levels into horizontal vertical, but the cross subbands are rotationally symmetric. We can perform the rotations also in case of cross subbands. So here we have four images. B represents original image. A represents the horizontal, vertical, and orientation split possibility of the input image. And C represents the four steerable filters applied on the image B is represented here. What it means each one is sensitive to edges but in different direction. The last one D is the result after applying the filter is shown in the subbands, which means the small images are in low frequency, which will be more blurred, and the big images are in high frequencies. So each image highlights certain edges of the original B image, and one may represents the vertical edge, another show the diagonal edge, another shows the curved edge, etc. So this is a multi-scale representation, multi-scale wavelet representation or wavelet decomposition. And the last one D, we can also state that it is over complete. Over complete means more detailed descriptions. Okay, over complete means it will having more detailed descriptions which can be useful for texture analysis, texture synthesis, as well as pattern analysis. Okay, this can be used for so and so tasks. And then application, the main application of wavelet transformation is image blending. So image blending means we can combine both images or combine two images, half from image 1 and another half from image 2. Combining both provides a blended image. So the Laplacian pyramid is used to create a capitative blended composite blended images. The key approach involves smoothly blending low frequency color variations between red and red apple and orange. High frequency textures are blended more quickly to avoid ghosting effects. So see this example. A image represents apple, B image represents orange, C represents the regular combinations. If we divide the image into two, we'll get apple, and if we divide the image into two, we'll get one part is orange. So on combining both, we'll get this. So when you apply the Laplacian pyramid image bending, so the result will be much better than this. Similarly, here the figure E represents the input image, figure F represents second input image. So G represents region mask. So in this region, I'm going to blend the original image E. Okay, so and the blend by low frequency. If the both colors as well as shape, the color as well as shape is blended using low frequency. The textures of both, here it is smooth, it is somewhat not smooth. Okay, so the textures are blended by high frequency. That's what mentioned the above. So smoothly blending low frequency means it preserves the colors as well as variations. In order to preserve the textures, high frequency is used. And the blending in details is represented. Here we have images from A to L. The first three rows show the high, medium, low frequency part. So the row 1, row 2 and row 3 shows that this row represents high frequency details of an image. Second row represents medium frequency. The third row represents low frequency. Low frequency, we have seen in many cases, low frequency means the result will be smooth. High frequency means the image details will be sharper. You can see from the high level image, the low level image produces very less details, but you can see the color is much better than the high level frequency. So on combining both, we can get both color as well as the sharper details. and the left and middle column shows the original apple and original orange images. So the A, B represents original apple and original orange. Here D, E also represents apple and orange. G, H represents apple and orange in high, medium and low frequencies. And J and K represents also apple and orange. The last one, the right column represents the combination of both apple and orange. That is the blended images in high frequency, low frequency, and moderate frequency. So the final resultant is displayed here. So this is a major application of wavelet and Laplacian pyramid. That is what mentioned here. So we will first take a binary mask of an image, and we'll construct the Gaussian pyramid from the mask, and each Laplacian pyramid is then multiplied by the corresponding Gaussian mask. The sum of these two weighted pyramids is finally shown in the last column. And the last one is image warping. So generally applying a filter will change the brightness or contrast, but warping changes the shape as well as position of the object also. So divide these images into two parts. Okay, so a normal image, on applying the filter, it will produces some brightness, or it will enhance brightness, or it will enhance the contrast. But the same original image, yes, on applying to the image warping filter, it will change the position. You could see the change here. So here in this image, the brightness is enhanced. Here the orientation is changed. That is what represented in the wave format also. And common difference between pyramids and wavelets. So it is image pyramids means it is a stack of progressively blurred and downsampled images. We'll use Gaussian or Laplacian pyramids. Here we'll use subband filters, low pass and high pass filters in four ways. We'll capture fine as well as coarse detailed also. And redundancy, image pyramids may have redundant details, but wavelet is non-redundant. The reconstruction is not exact. When you reconstruct the image to original, a wavelet will produce perfect reconstruction. Orientation, no explicit orientation is possible, but in wavelet we can divide horizontal, vertical, and diagonal representation. And the image pyramid can be used in yearly CV tasks. And in case of wavelets, we can use in modern CV tasks. Thank you.